I'm Luke Seibold, this is PhyziX, and today we're going to be describing motion. Alright, so there are a couple different ways in which we can describe the motion of something. The first two being distance and displacement. Now, you might sort of use these interchangeably when you're talking about them, but in physics, they actually have quite discrete definitions. On one hand, distance is what we call a scalar quantity, so that means it only has magnitude, meaning it only really has an amount. Now, on the other hand, displacement will have both a magnitude or an amount and also a direction. So that might be north, south, east, west, or it might be defined by an angle. So let's first take a look at distance. So let's imagine we got a car over here, little car, and it's trying to get to point X over here. Now, the road that it has to travel snakes like this. It goes all the way up and around and down and through, and it's winding back and forth, and it goes backwards and up and down, and finally gets to the X. Now, the distance it traveled would follow this road. So let's say this road in its entirety is 50 kilometers. 50 kilometers. So if we remember from standard units, that is 50,000 meters, or 5 times 10 to the 4 meters. Now, on the other hand, you have displacement. Its displacement is just how much it's been displaced from point A to point X. So instead of counting all this movement that it's done winding through this road, it's just the displacement between where it began and where it finished off. And so that displacement would only be, let's say, 20 kilometers, or like we said before, 20,000 meters, or 2 times 10 to the 4 meters. And now also, because it is a displacement, we also have to give a direction that it's in. If we're saying that this is north, this is east, south, west, then it's going roughly northeast. Alright, so here's another little interesting thing about the difference between distance and displacement. So let's take a look at the orbital path of the Earth around the Sun. I know this isn't to scale, but let's just take a look. So here we have the Earth, and it's traveling all the way around the Sun in a year, and the orbital path is actually 940 million kilometers. And so when we see kilometers, we multiply it by 10 to the 3, and when we see million, we multiply that by 10 to the 6. So altogether it's times 10 to the 9, and then the other two makes it 9.4 times 10 to the 11 meters. So the distance that the Earth traveled as it travels around the Sun is 9.4 times 10 to the 11 meters. But its displacement in 1 year is actually only 0, because it hasn't displaced itself at all. It's in the exact same place that it was 1 year ago. So even though it did all that work to move 940 million kilometers, its displacement is still 0 meters. All that for nothing. Alright, so let's summarize what we've just learned. So distance is measured in meters, and you'll sometimes see it referenced as a little d. Now, displacement sometimes be represented by d or an s or even an x. Even an x is also measured in meters, but the definition would be the vector distance. So just like distance and displacement, we also have a difference between speed and velocity. Now, speed is a scalar quantity, while velocity is a vector quantity. So this means that speed is the measure of distance over time. So because distance is measured in meters and time is measured in seconds, then the unit for speed is meters per second, which can also be written as m times s to the negative 1. Now, displacement is also measured in meters and time still in seconds, so the units for velocity is also meters per second. Now, if we go back to our little orbital model of the Earth, we can calculate both the speed and velocity of the Earth as it travels around the Sun. So first let's calculate its speed. So we know it traveled 9.4 times 10 to the 11 meters, but how long did it take it to do that? Well, we all know how long it takes for the Earth to go around the Sun. It takes a year. So, but first we gotta translate 1 year into seconds. So if we know that 1 year is equal to 365 days, we can cancel out the years by multiplying it by what am I saying? By multiplying it by 365 days over 1 year. So that cancels out the year, and you're left with just days, which gives you 365 days. Then how many days are in a year? Well, we have 24, or sorry, how many hours are in a day? We have 24 hours in a day over 1 day. And then you can cancel out days. Then how many minutes are in an hour? Well, you have 60 minutes in 1 hour. Then you cancel out hours. And finally, to translate it into seconds, you got 60 seconds per minute. And cancel out the minutes. So then you do all those calculations, which comes out to be 365 times 24 times 60 times 60, and it gives you 3.15 times 10 to the 7 seconds. So if we take this figure and divide it by 3.15 times 10 to the 7 seconds, we get 2.98 times 10 to the 4 meters per second. But let's go back over to displacement. Now, the displacement is still 0. So it doesn't matter how long it took to get back to its initial position, the displacement is still 0. So even if it made even if it traveled all that distance in 1 second or 3.15 times 10 to the 7 seconds, it wouldn't matter what it is. So even if it was 3.15 times 10 to the 7 seconds, it would still always be 0 meters per second in terms of its velocity. Alright, now let's throw what we've just learned into our little table. So speed, which can be represented by sometimes a V or also sometimes a U, is measured in meters per second. And that's because it is the rate of change of distance. Now let's add another little column for equations. So because we know that it is the rate of change of distance, it is the amount of distance that it's traveled in meters over seconds, which is time. So from this we can derive the equation that speed is equal to distance over time. And now let's do velocity next. So velocity, which can also be represented by a V or sometimes a U, and because it uses the same units, it's meters per second, but in fact the definition differs in that it is the rate of change of displacement. We'll give it velocity is equal to displacement over time. So just to differentiate the variables a little bit so that we know which one is which. Velocity is displacement over time, while speed is distance over time. Alright, so finally we have acceleration. Now, acceleration is defined as the rate of change in velocity over time. So that means that acceleration is equal to velocity over time. Now, we know that velocity is equal to displacement over time, so we can sub that equation into here, take this part and put it into v, and we get acceleration is equal to displacement over time, or displacement over time squared. So what are the units for acceleration? Well, we know the units for displacement are meters, and the units for time are seconds. So it is meters per second squared, which can be written as meters times seconds to the -2. So what exactly is acceleration? Well, the most common place we see it is with gravity, the acceleration due to gravity. And this can be seen whenever you drop something. So let's say we got a little dude over here, and he's holding out an apple. He's holding out an apple over a cliff. I don't know why, but he's just doing it. He's got his little apple in his hand. He's holding it out over a cliff. Now, when he drops the apple, it initially has this much velocity. We're going to represent velocity by this little vector. So the arrow is pointed in the direction that the velocity is headed, and its length represents its magnitude. So at this point, it's going this fast. But once it gets to this point, then the velocity has increased. Right? When you drop something, it gets faster and faster the further it gets from your hand. And so this means that because the velocity is changing, because acceleration is the rate of change of velocity, that means that the apple has an acceleration. And the value of this acceleration is represented by the acceleration due to gravity, which is often given as g, which equals 9.81 meters per second squared. So what this means is that the apple is increasing its velocity by 9.81 meters per second every single second. Alright, so finally let's add acceleration into our little table. So here we go. Acceleration, which is usually given by a little a, which the definition for acceleration is the rate of change of velocity. So this is given in meters per second squared. And so the equation that we have for this one is acceleration equals velocity over time. So there you have it. Now you should be able to accurately describe how an apple falls, or even how the Earth moves around the sun.